also wasn't as efficient as we wanted it to be. It was only in the percent level. So, but what it did open up, which is just wonderful from a basic research point of view, is that it opened our eyes to the entire body of literature that we could draw upon to make a technology on silicon color sensors that just went by a different name, right? So one of the things that is just from a timing perspective is perhaps unfortunate is that there's been a lot of work on looking at luminescence sensors in silicon from the perspective of damage research, right? So radiation damage centers were an intense focus of interest in the 70s and 80s, as you might imagine, when silicon went through kind of its big R&D cycles. And there was a lot of work done to understand what defects were being formed when the silicon was damaged by radiation for the purposes of launching silicon into space, as another condition, right? So just stress testing this most important material, commercial material we have, really. And so there's this giant body of literature that you can go and look up, and you're like, okay, well, what is this transition? What is this line from? Where is it? And you can go and from these lines, go and take a look at the body of literature that's showing you, 10, 20 publications that you can look up that tell you all sorts of stuff that was known and studied very deeply in the 70s and 80s. So what we did is actually just surveyed that literature and found a whole bunch of really exciting stuff. So I'll talk about a few. Basically, they're similar in what you want to think about in terms of NVs, let's say, or silicon carbide defects, in that there are known contaminants within almost all silicon to very low levels, right? It's a clean material, but everything to a very, very low level, you'll get some contamination. And so like carbon and oxygen and hydrogen just exists within silicon. And so if you just damage the lattice with any amount of implantation and do appropriate heat treatments, you can form all these known defects. And through detailed studies in terms of their local vibrational modes and all sorts of like optical characteristics, you can figure out a lot about what these things are and what their properties are. So we took a look at some of these defects. Now that we're armed with silicon-28, we can get a lot more out of it. And so our first work into this direction was on the so-called C, G, and W centers. These centers is, again, it's a throwback to the 70s and 80s, where what was initially happened is they just damage silicon and see what came out. And then before they were identified, their chemical constituents, or rather their atomic constituents, they're labeled with this alphabet soup labeling scheme, right? And so there's an M center and a C center, and so you can go back and look them all up. And so we're adopting that language. Now, the easiest to generate centers, I would say, in silicon, at least the silicon-28 that we had, use natural constituents that exist within the crystal, including carbon and self-interstitials. And so we characterize the C, G, and W centers in this paper here, and I encourage you to go take a look at them. They have interesting applications for each of them. So as you saw with the other phosphorus donors, if you take this broader line that you see in natural silicon, which is again known to already be incredibly sharp, and you move to a silicon-28 environment, you have dramatic narrowing. And so the homogeneous environment or near homogeneous environment for some of them are very interesting. C is, of course, particularly interesting because of how close it is to the telecom band. It does have an excited state triplet that you might be able to use, but it's a relatively slow emitter. The G center was a very interesting one in that it's easy to make. Oh my gosh, it's easy to make. It's almost impossible to get rid of. It's so easy to make. It's very bright, very short-lived lifetime on the tens of nanoseconds. And for the first time, we learned a little bit about what possibly exists as an orbital structure, because this was completely hidden in this inhomogeneously broadened environment. And so the G center has been since pursued by some researchers in France. And as an emitter, it's actually a really promising center. And W center is another one. This one's pursued now by NIST. It's again, one of these things that it's a little bit more sensitive to the environment. It's a triple interstitial or triple self-interstitial. But the take-home point from all of these things, even if it's a relatively bright emitter, is that none of these have a ground state spin, right? So these are great emitters, and one of the things that people just didn't seem to believe was that silicon could have good emitters in telecom. It does. They're here. They're easy to make. But what the challenge is there any of these that could offer quantum information storage opportunities with a spin? And although they do have some nuclear spins, like for example, you could imagine figuring out how to access the spins of these nuclear spins of their carbon-13, for example, that handle isn't really easy. It's not an easy in. fortunately, the T center is. And so for the rest of this talk, which I have to apologize, I am talking a little bit at pace here to try and get through things with the delayed start. And so I'll take questions at the end, but I'll tell the rest of this talk is going to be about the T center. So we have a nice big PRX quantum paper that talks about this T center at length. There was, again, a lot that already existed in the literature, but not in the context of quantum information, because it just predated the interest in quantum information. So the T center itself as a structure is 2 carbon and a hydrogen, and it has an unpaired electron in the ground state, which is just phenomenal, and which we'll find ends up being just as good as you see for any other unpaired electron spins in silicon, basically. So it also goes through this kind of dramatic narrowing. So if you take this natural silicon, this inhomogeneous broadening dramatically narrows to this not homogeneously broadened line, but very narrow. It's on the order of tens of megahertz. And the center itself, it's right in the O band. And so you can also use this to characterize now that you can drive it, you can drive the ZPL, you can measure the sideband. So you can pump resonantly and measure its so-called Debye-Waller factor, which matters for some people that are trying to get into the nitty-gritty of these kinds of centers. So the Debye-Waller factor for this center is about 23%. And so you'll ask, okay, well, is this really a telecom center? And the answer is definitely yes. So this is the O band, this is not C band. And this is actually kind of deliberate. There is a family of centers. That's the T, I, and the M centers are all very closely related. They have the same kind of core and then different kind of configurations. And the I center has an extra oxygen. And they emit at different wavelengths. One is at the 1600 nanometer mark, the M center. But what we thought would be important and what we really like about the T center in particular is that it's quite close to the zero dispersion wavelength point for single mode, for the dominant single mode fibers. And it's also, the O band is just as easy to find stuff as it is in the C band. And it is the band of choice when you talk about data center connectivity. So that's one of our motivations there. So what is this thing? Well, I told you atomically what it is, but what is the level structure here? So the excited state is an exciton, right? So the ground state is this unpaired electron spin, and the excited state is an exciton. In silicon, the exciton is going to be an extra electron and hole. And so the electrons pair up and they form a singlet. And so the only thing that's magnetically defined is the hole in this TX state. The hole itself experiences the effective strain of the center to form 2 doublets. So the hole is naturally 3 halves, and it gets split into 2 doublets, and which we call TX1 and TX0. And the nice thing about this is that the splitting to the between these states is relatively large, so you don't actually get that many thermal excitations between these 2 things at reasonable temperatures. So at 1.5 Kelvin, for example, there's no excitation whatsoever, and you can think of this as quite simply a 1/2 by 1/2 system in terms of optical transition. So you have a lifetime that's kind of in a Goldilocks regime, I'm finding, actually. So it's not too dark and it's not too bright. So there are other color centers in silicon, which are, maybe erbium or these other things that are just very, very dim. They spit out, maybe a couple hundred photons per second. But if we're talking about this, it's sub-microsecond, which is good. And it means that if you put it into a Purcell, if you use the Purcell effect in a cavity, you're not working in the few picosecond regime. Okay, so magnetically, whoa, this is what we get. So you have, if you put a magnetic field, we have these doublets, right? I was saying that there's a spin 1/2 effectively in the TX0 state as well as in the ground state. What we find is that the ground state is isotropic. It has the same splitting regardless of orientation. But the excited state has all these different orientations, or rather it has a different splitting. It has a different effective G factor for its different orientations, because that's the cost of doing business. If this thing is, as many nuclear spins as it does, its orientation relative to the magnetic field gives it up to 12 different orientational subsets. And so the anisotropic nature of the G factor of the hole in the excited state gives rise to all kinds of splittings, right? So we have all 12 different orientational subsets. We have spin-dependent splitting or spin-dependent optical transitions for each of these, right? So you can see A, B, C, D transitions for all 12. And within those levels, although you can't see them optically because they're just too small for the fields that we're working at, you have all the spin information that you can use, right? So I've already referred to the unpaired electron spin, but of course, you have that hydrogen nucleus that's there always for you for free. And then at your discretion, you can implant carbon-13 and get extra nuclear spins or not. So yeah, that we have quite a level structure that we can play with. Optically, if you go and take a look at these things as an ensemble, you'll have 4 transitions for all 12 orientations. So you get up to 48 lines. And that is exactly what we see. So this is the luminescence as a function of the field. What you get is all of these quartets of lines, right? So A, B, C, D, and they're going to see these different splittings, even if the ground state is splitting the same way the excited state is not. And so you get all of these different interactions. But that means you can go and pick an orientation and measure it and measure its T2 times and the rest of it. And we show that these things are highly competitive spin qubits as well. So for the rest of this talk, I'll just focus on just that one orientation for these bulk measurements. These are luminescence measurements, right? So we're just generating piles of excitons and it's just generating light for all of these different orientations. What you want to do is also characterize how to behave, how to control these things if you're driving it directly, right? So we're going to put a laser onto, say, this transition and see what we get. We're going to use it to actually measure the spin and show that the spins are very well behaved as you would expect within silicon, or rather as I've come to expect from high quality silicon. Okay, so what you get is not that forest of lines, right? So if you're to actually just take a laser and drive it over that, you don't see really much of anything. And the reason for that is that if you sit on one of those 8 spin selective transitions, what you end up with is quickly you're hyperpolarizing your system and very efficiently, right? So what you're doing, so for example, if you're driving the B transition for one of those orientations, what you'll end up with is as the exciton falls back down to the ground state, because it doesn't seem to bleach. This isn't a bleaching issue. What it is actually doing is hyperpolarizing into the other spin state that you're not addressing with your optical field. So to be able to recover some of the signal that we've seen in the previous luminescence results with this direct driving is we have to depolarize things, right? So in these experiments, we chose to depolarize things through the combination of microwaves. So what we did is we applied microwaves to the system. We knew roughly where it would be because, of course, these are all G=2 sorts of systems and in the ground state. And that depolarized things. And so that recovered some of the optical signal. So for example, at this low field that we used, if we drive with just one microwave tone right in the middle of the G=2 kind of pair, rather than these 2 split colors here, you'll get this gray trace. So one of these traces here is what you get if you're driving right kind of in the middle. And then if you start splitting those 2 microwave transition frequencies and considering more than one frequency, you get this different recovery, right? So you get this green trace here. So you can actually see a different recovery in signal depending upon what microwaves you're using. And what that's telling you is about the hyperfine interaction. It's telling you that the hyperfine interaction actually is anisotropic as well. So again, we're going to stick to this one orientational subset, this choice 1 here. But it's just to say that we're learning a lot about what the system actually can offer. And it's nice that it actually has this anisotropy in hyperfine interactions, which I can get into if anybody cares about. Okay, so what does this give? This means we can start measuring our spins, but the obvious way to do so, or at least maybe the naive way of doing so, isn't the way you want to go. If you wanted to just say measure the luminescence from one of the 2 different spin transitions, what you get is a hyperpolarization problem almost. You don't have cycling transitions. What you get is if you're driving one spin state, you're hyperpolarizing into the other one, and so your system's gonna go dark really quickly. So if you're going to be just trying to measure the electron spin directly, you're kind of in a tough spot, because what we find is that actually it's hyperpolarizing almost at the same time scale that our shutter was opening, right? So we have to kind of think about something a little bit differently. And so what we did is we actually took a look at the nuclear spin as the observable, as our quantum observable. So what that meant is that, you know, if we're trying this kind of sequence, right, where you have basically 3 of your levels in directly or indirectly accessed by the laser, ultimately what you're going to do is hyperpolarize everything into this spin state here, right? And then, so that could be your preparation stage. If you then flip into this collection phase where you flip which microwave is being applied, what was hyperpolarized into this state will go through effectively a cycling transition many times before it hyperpolarizes into the other one. It'll either generate a photon direct, or it'll be through the microwave, pop down here and then go through a optical cycle and come back down to the ground state. And it's not clear which electron spin state is populated, but the nuclear spin hasn't flipped, right? So eventually it ultimately doesn't matter which electron spin state you populated here, because both will eventually go and send out a photon again. And so that optical cycle can happen many, many, many times before the nuclear spin finally decides to flip. And that's what you see here in this red trace, like this very, very long tail. And so that is the observable that we use to measure our spin. So we're going to be measuring the hydrogen spin directly. And in doing so, once you get your readout, you're off to the races, right? We already have microwave control over everything and RF control. So we just went and take a look at T1s and T2 times. And as is the case for basically everything we measure in this particular rig, it's limited by the rig, not the qubits. So these numbers are definitely lower bounds because we know we have magnetic field noise, and this is very much a DIY system where the inhomogeneities on the magnetic field and the rest of it are just, you know, we do what we can. But yeah, even then, the T1 we stopped measuring it. And that's informed by other unpaired spins, like the T1 for unpaired electron spins at these temperatures in similar systems is like weeks, hours, days, like somewhere in there, depending upon the specifics. So we just stopped measuring. For the T2, we just did a Hahn echo. And if you take a look at just the average, we see this characteristic decay, which is indicative of the fact that we have a magnet problem, not a qubit problem. We've seen this before. Same thing with you can measure the nuclear spin, the T1 and the T2 time for the nuclear spin. We have a first guess at mitigating the damage from this magnetic phase noise is how it's termed. And in doing so, get a T2 time of over a second. But again, we think this is something to do with the magnet and not the spins, because that's just typical of what we've been seeing so far. So yeah, that was all in that one paper. We put a whole bunch of stuff into that one paper, where prior to where we started, not very much was known. Like we knew the atomic structure was known, some basic recipes for fabrication were known. The atomic constituents were known, and the zero phonon line width was known. But for this color center, there was a lot else that wasn't really known. We know that the homogeneous line width is less than 30 megahertz. It's probably, you know, a good factor of 3 less. We have a Debye-Waller factor now, as well as a lifetime and some T1 and T2 numbers. So really everything looks good. This is like click, 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 or rather from a checkbox perspective, tick, 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 in terms of let's go and build a technology off this. Let's go see what this looks like in real devices. So that's the next, I hope 10, maybe 15 minutes of this talk. I'm going to try and give a few minutes for questions at the end. But the next bit I'm going to talk to you about is relatively recent results where we are able to integrate a whole pile of these things into integrated photonics, and they seem to perform pretty well so far. So we, just to remind you, silicon integrated photonics, you have this device layer, which is a couple hundred nanometers thick, and the reason why you choose that, that's an industry standard now, it's so that you can have single mode features at telecom wavelengths. And so if you implant a whole bunch of carbon and hydrogen and you do some annealing treatment, which has been it's in this archive paper if you want to go take a look, you have different ability, or quite an easy way of making these things, right? You can make them in very high densities. And what we're doing when we're making these in very high densities is very damaged material, right? So these are very much first go, where we just made a pile of it and we're able to generate it quite successfully. Oh, I'm not sure if you might want to mute, Arthur. We just heard you sneeze. So we were able to generate quite a bit of this. And fortunately, the SOI material, where we're able to just probe that silicon photonic layer, generates piles of T. So this is the T line here, and you see the sideband. And you can see on the trace here that there is still some damage. You get broad damage background that's around this. And importantly, the irradiated material that was used when we took a look at this in natural silicon isn't so different in line width from the implanted material. So the irradiated material, of course, here is using carbon-12, but the implanted material, it's a little bit broader. The shift is due to the fact that we implanted carbon-13. So we don't actually have a massive inhomogeneous broadening when you move from irradiated to implanted. So that's encouraging. What we were able to measure when we first created this was some characteristic spectral diffusion, because of course, the challenge when we're talking about integrating color centers into things more broadly is, well, how do these things behave near interfaces, and what do the optical properties do when you're so close to an interface? And it seems like we have a method for characterizing the spectral diffusion of an ensemble, which is a helpful tool for helping us iterate and improving this metric. So what you can do is you can actually we have this inhomogeneous broadening, right, when we're working with natural silicon, where these are static inhomogeneous broadenings, wherein it's just to do with the fact that the specific silicon-29 is nearby or not. And so you can effectively park your laser on one part of this broader inhomogeneous line, and as a function of field, see how the signal decays. And what that does is, if you have spectral diffusion, which is just basically the property of the optical line to like wiggle, right, how much it moves around. If you're at a small field and that spectral diffusion changes the line, when you're in a small field, the electron spin splitting, you're not able to just hit one of the two lines, right? You're not able to hyperpolarize things because the spectral diffusion is going to kind of drive it back and forth. So you'll be hitting both of the lines as it moves around. And so even though you're in this inhomogeneous broadening limit, you can measure the effective characteristic spectral diffusion by seeing how quickly the signal decays as you put that field on, right? So if you have a lot of spectral diffusion, it'll take a long time for it to decay. If you have only a small amount of spectral diffusion, it should decay relatively quickly. And so we have bounds for both the silicon-28 as well as the natural silicon that we're looking at the few tens of megahertz in spectral diffusion, which is, those are good numbers. They'll be good enough to engineer around for a large scale technology. In the SOI, it's a different story. So our first it's near amorphous, this material. The spectral diffusion is closer to a gigahertz. And so, yeah, one of the things we get to iterate on over the next little while is taking that down. But again, this is the first generation material. So we're not in a bad place, but we're going to improve that as time goes on. Okay, so let's go and take a look at some singles in the few minutes we have left. So one of the things about silicon, which makes it great for integrated photonics, is the fact that we have a high index of refraction. So all of the optical components are pretty tiny. You can make everything, small and control it, and the mode confinement is quite high because you have good contrast. But what that does mean is that total internal reflection kind of messes you up if you're trying to take a look at these things within say a confocal microscope, which is the standard of choice when you talk about, say, ND centers. The others, you can go and take a look at individual centers relatively easily because of how bright they are and how easy it is to get light out of even a relative index material like diamond. But silicon is just a lot harder, and so one of the things we had to do is think carefully about how we're going to try and see singles optically. And so this paper here is the first optical detection of spins in silicon. And we were able to do this by doing some really like zeroth order optical engineering by etching away the device layer of the silicon into these pucks, right? So in true Canadian style, where what it does is it changes not very much in terms of Purcell factor. It doesn't change the lifetime of the spin of the optical transition very much, but it does change where the light is going. Really, you're no longer the total internal reflection, which guides it into the device layer, is removed, and so it has this preferential emission in the vertical direction. And so what we did is we printed a whole bunch of these things. We have, I think this chip has 30,000 of them. And these are just little pucks. And so what we did is we started with that SOI material, and then we etched it all down, and we have these pucks left over, and the T seemed to survive that etching process, no problem. And it didn't actually even change the characteristic spectral diffusion, as we'll show. Okay, so yeah, you go and take a look at each of these. We can put a confocal microscope on top of these and take a look. This is just one patch, right? So we have, again, more than we'll ever want to measure for this particular chip. But what we have is a whole bunch of individuals. And so you go and take a look at each individual puck, which had a relatively high concentration. You can see all these individual zero phonon lines. And so the inhomogeneous broadening is, much, much broader than this. And so you're seeing the individual centers within those pucks. So we just picked 3 individual pucks here to plot them all out, but every single one of these pucks had on average one and a bit T center lines. And the characteristic line width here matches that characteristic spectral diffusion number that we calculated in that earlier paper, where it's about a gigahertz. So we have a whole bunch of data on, well, I mean, this patch, we have a bunch of data on a lot of them, but basically we have some thermal broadening that we would expect at these higher temperatures around 4K, 5K. We have some power broadening that we would expect if these things are efficient centers, which we suspect they are. And we also have this additional spectral diffusion that's adding up to give us the characteristic line which we see, right? So if you go and you take a look at all 144 pucks here, which again, I mean, they're not entangled with each other, but that's a lot of qubits. They are entangled with the photons they're emitting. So that's an encouraging opportunity. We can take a look at their individual characteristics. Their line width follows kind of what you would expect for that spectral diffusion measurement that we've done. And you can see that within pucks, the inhomogeneous broadening is more. Like, so this black line is the distribution of T as in the bare SOI material, the pre-patterned SOI material. And so you do get strain effects messing up some of those higher wavelength qubits or higher energy qubit transitions. But yeah, it's all about where we expect it, which is great. And so that's each one of these is a bunch of singles that you can go and target. And one of the nice things about this is that they seem really stable. They don't bleach, they don't blink, they just kind of rock solid. So that's quite nice. You can apply a field. So what we did is just in the last little bit here, you can apply a field, and because the excited state has this different this anisotropy to it, you can actually get different. You can see the spin, the signature of the spin, differently in each of them. So this was one constant magnetic field where we took a look at different centers. And these different centers have different orientations with respect to the magnetic field. And if you remember, what that did is it changed the excited state splitting differently. So the ground state splitting is the same, but the excited state splitting is different. And so when you take a look at these things in a magnetic field, we're using the same kind of idea we were borrowing before, is that if you're to just drive it with one frequency, you don't see anything. Because you get this hyperpolarization, right? If you're to scan over A, B, C, D, you get hyperpolarization. So to actually get some kind of cycling happening and detect a spin optically, you'll want to have some depolarizing scheme. And in this case, we didn't use the microwave side, but we used a second laser, right? So we had two lasers, two different wavelengths here. And basically when the combination of the two lasers gave rise to signal, you can see the spin. And so in some instances, say here, the G factor, the effective G factor of the excited state for that spin is about the same as the one that you got in the ground state. And that's why it doesn't really matter what laser frequency you're using. So long as one of them is hitting that frequency, you're hitting both B and C at the same time. So you don't see hyperpolarization. And so that's why you get signal there. For some of the other centers at the same field, right? It's the same field, but they're oriented differently with respect to the field. You start to see these combinations show up, right? Where you have B and C need to be at different frequencies to actually get you the signal and an optical cycling transition. So this is the signature of a spin, the spin of these T centers. And so if you take a zoom out, you can actually see from that same plot there, if you take a zoom out, you can actually see all four A, B, C, D transitions, right? So if you look at the cross section on those four different segments there, it's effectively the same thing as parking your laser, one of your lasers on one of the transitions, and then sweeping the other. And you can see, for example, if you're pumping A, then B and D show up, which is what you would expect, right? If you're pumping A, then B and D are the ones that depolarize your spins and give you that cycling transition. So wonderful. It's really encouraging that we can go and just take a look at spins individually this way. We know that, of course, these are singles for a whole bunch of reasons, including the fact that if you happen to have overlap spectrally, that you would almost certainly not have, in addition to that, overlap from an orientation perspective. So it's just nice to move forward and start working with these things into integrated systems where you can have higher collection efficiencies. So with that, this was a pre-COVID picture. You can tell my hair is different, the team is different, but I had to show some smiling faces with it, not a Zoom call. So the actual team that's in the lab right now is up there. we're all based here up at SFU Burnaby Mountain, which is in Metro Vancouver. Sometimes I like working on a mountain. The air is really nice, and sometimes you get to look out over these inversions where you get this sea of clouds out over the ocean. So it's just wonderful. And if you want, after all of this madness, lockdown madness is over, we're here. Come visit. Come have a look. And I would be remiss if I didn't mention that we're very excited about this technology, and one of the ways we're excited about it is the commercialization potential. So there's a lot of research that needs to happen, but there's a lot of development that's happening alongside. And so that's through this company, Photonic, that's again based in Metro Vancouver, and we're really kind of moving forward quickly on both fronts here. So just more broadly, if you want to come and be a part of this effort on both the academic or the commercial side, please do give me a shout. I'd love to hear from you. So with that, I'm going to turn it over to questions.
Thank you so much, Stephanie. That's fantastic. So I think you're all allowed, or you're all able right now to unmute yourselves. So if you can, if there are any questions, please feel free to do so. If you prefer, you can just write them to me in a chat and I'll be able to ask Stephanie. However, time is of the essence because Stephanie's only with us for another 12 minutes, unfortunately. Is that correct, Steph?
Yeah, I have a hard stop, sadly.
So can I ask a question?
Yeah,
please.
Okay, so how are you going to make a quantum computer out of this?
Yeah, so the modules are going to be linked photonically. I don't want these things talking to each other nearest neighbor. That's a nightmare. I've been there. I don't want to do that. So the idea is that you can have universality by generating entanglement through optical mechanisms, which has been demonstrated in a number of different color center systems in a number of different ways now. There's reflection and emission schemes, and that's your primitive. You can do everything universally that way, and then you don't have to worry about nearest neighbor crosstalk nonsense.
Okay, so each of these little pucks you've got, how many spins, how many color centers are there in each? And that's going to be one.
I mean, like we wouldn't be using pucks. We have all of integrated photonics. This is just that's just a microscopy or a microscope deliverable. Like what you do is you integrate these things into cavities that improve their optical emission properties. You get some Purcell to make them faster, and then you send the light into switches that entangle whatever ones you want to entangle, right?
Okay.
Right. Or you use cavities and get reflection, right? You can reflect cavities, or you can reflect photons off of cavities that are loaded with these centers. And those are other approaches that have been worked at in other color center systems.
So this is just single photon sources that, I don't mean it's just, I mean, you understand it's I'm not trying to slide it or anything, but there won't be actually entanglement of the centers themselves.
Oh, of course there would be, yeah.
Well, how?
Well, okay, so the photons that are emitted, like just think NVs, right? Think of everything that the NV platform is trying, like if that's a helpful mental model, right? They've done they've set up multi-node networks where you actually get photons that are entangled with the spins they leave behind.
Yeah.
Right, and then you get entanglement swapping back to those spins.
Yeah.
And then you have everything you need, right? That you have universality that way.
Yeah, okay. Modulo all the detector efficiency issues, but yes, sure.
Well,
okay.
The point about putting it into the spins then is that if you lose a photon, who cares? Try again, right?
Yeah.
And these things last for ages, right? They're very long-lived objects. So,
have you demonstrated any sort of entanglement between spins with tomography and all that stuff?
It's in the pipeline for sure.
Thank you, Steph. So I have a quick question if nobody else has any pressing ones. Do you have a feel for the efficiency of the interaction of the entanglement with the photon, between the photon and the spin? So do you need very high Q cavities and such? There might be some trade-offs.
Well, those are two different questions. Sorry, which one do you want me to tackle?
The first one first, yeah.
Yeah, so the efficiency, these things, I think they're upwards of 10% efficiency already. I think that somewhere between 10 and 100, right? There's a bit of back and forth on that. So I'm not going to pin myself to a number, but it's somewhere between those two, I think. And that's enough, right? Like you put it into a cavity, you can really drive that to whatever efficiency you really want. At that stage, you care much more about loss in the network overall. And the cavities that you can get away with to do that, like 10 to the 3, 10 to the 4, 10 to the 5. I mean, silicon can demonstrate 10 to the 7, 10 to the 8, right? So At that point, it's much more about reproducibility rather than the actual Q factors.
Thank you.
Yeah, no problem.
Any other questions by anybody else?
Oh, I talk too fast, that means.
No, just, I mean, yeah, it was just the extra like 7 minutes or so that we took initially to switch and stuff, but overall it wasn't too bad. It was just extra 3-4 minutes. Anybody else for any questions? Okay, sounds very good. So how can you, so this final question, how can you divvy up the work between the science and the group and the development in the company?
Yeah, there's a lot to do, as you might imagine, right? So there's a lot of development that is really best suited, a lot of engineering that is really, you know, it requires a steady hand, kind of more engineering focus, and then there's the more exploratory effort on the research side, and both need to continue because first generation is not going to be the final generation, and we need to be able to allow for, you know, the fundamental research around this space, as well as the commercialization arm to really drive home like yield questions and stuff like that, which is, you know, much more appropriate for in a commercial setting. So it's a highly complementary, highly integrated team, where the division of labor is kind of around those angles, right? Research versus development.
I see. Sounds good. Sounds very exciting.
It is.
Well, if there are no more questions, or are there? Okay, if there are no more questions, please help me in thanking Steph for making the time to talk to us, and help me also in keeping her to her promise to come and visit when everything improves. Thank you so much, Steph. We appreciate it.
Thank you very much, Stephanie. It's very nice to meet you and very nice talk. Thank you.
Thanks so much. Have a good afternoon.
Yeah, same to you. Bye-bye.